Hello dear students, welcome you all. This is 𝐂𝐚𝐴 Rathore and this is one shot series. We are going to discuss properties of materials in this class. So only one topic, properties of materials, but properties are many. There are 15-16 properties that we are going to study. First property is elasticity. So as you know, if we are having any material, if we apply load, there will be some deformation. In an ideal material, suppose we are having a material that is ideally rigid. So in a rigid material, but that rigid material does not exist in reality, that is a hypothetical scenario. So in that rigid material, whatever load we apply, there will be no deformations or no strains, right? But in a real world materials are deformable. So when we deform any material, there will be some strains or there will be change in shape and size. Now this is because of the applied load and the material is resisting that load, so stresses are developed in the material. Now when we remove that load, what will happen? After removal of load, that material will either regain its original shape and size, either regain its original dimensions, or it will remain in the deformed state. So if that material regains its original dimensions or original shape and size, then we will call that material as elastic material. And if that material remains deformed, that means it does not regain its original shape and size after unloading, then that material is called as plastic material. Okay, so very simple definition, elasticity is the property by which material will regain its original shape and size after the loads are removed. Okay, clear? So any example of elastic material? Suppose you are having a steel ball. Okay, so steel ball, if you deform it a little bit, what will happen? It will, after removal of the load, it will regain its original shape and size. Or better example, in childhood days you must have seen that spring in the jetter pen. Okay, that stitch pen, jetter pen. So if you take out that spring and if you deform that spring, okay, so when you apply the load, there will be some deformations, but after removal of load, it used to regain its original shape and size, its original dimensions. Okay, so that material is called as elastic material. Okay, and this property is called as elasticity. So I hope elasticity is clear. So let us write down the definition. So elasticity, it is the property by virtue of which a material regains its original dimensions or you can also say it regains its original shape and size. So original dimensions or original shape and size after removing the load. Okay, so elasticity, it is the property by virtue of which the material will regain its original shape and size or original dimensions after load is removed or after removing the load. That is elasticity. Now at the same time, okay, okay, this is the property, and the materials which exhibit this property will be called as elastic material. Okay, so opposite of elasticity is plasticity. Okay, so if I apply load on a material, definitely it is going to deform, but after removal of load, if it does not regain its original shape and size, it remains deformed, then that material will be called as plastic material, and this property is called as plasticity. Any example of plastic material? For example, in childhood days, you used to play with clay. Okay, that clay soil mixed with water. Okay, and you used to make some pottery out of it. So when you deform it, it remains deformed. Okay, it will not regain its original shape and size. So that type of material is called as plastic material. Okay, so plasticity is also very simple. It is the property. It is the property by virtue of which the material will not regain will not regain its original shape and size or its original dimensions on removal of load. On removal of load. So this property is called as plasticity, and the material that will be exhibiting this property will be called as plastic materials. Okay. So elasticity is clear, plasticity is clear. These are very simple definitions. Many objective questions are asked on these properties of materials. Okay. So match the following and all those types of questions are there. So one-liner questions are mostly asked. So you must remember these, and these are important for all the types of examinations, right? Next property is ductility. Now, what is the meaning of ductility? Suppose we are having any material, okay, let us say we are drawing the stress strain curve of any material, okay. So, if I draw stress strain curve of any material and the stress strain curve comes out to be like this, okay, and let us say up to here we are having the elastic limit, okay, up to here we are having the elastic limit. So, this is the elastic limit of the material and this is the plastic range. Plastic range. Okay, so generally ductility is defined as the property by which we can stretch a material into thin wires. We can stretch a material into thin wires. Okay, generally it is defined like that, but if we go more technically, then that property ductility is the property those materials which are having large plastic range are called as ductile material. The materials which are having large plastic range, they are called as ductile material. So what happens with the large plastic range? When the material is having large plastic range, then that means they can be deformed. Okay, and that deformation will be permanent. Okay, suppose just an example, if I have a material which has stress strain curve like this, I have a material which has a stress strain curve like this, okay. So the strain at time of failure is very less. You can see material is failing at this strain, okay. So if I apply the load and it will break, okay, at very small strain it will break. Can it be drawn into thin wires? No. So if I have this material and if I start stretching it, so if it has large plastic range, then what will happen? If I keep on elongating, the diameter will keep on decreasing, and before fracture it can undergo large strains, okay. So that means it is more ductile and it can be deformed into the shape of thin wires. But what will happen to this material? If I start stretching at very low strain, it will break, suddenly break, okay. So this material cannot be deformed into cross section of thin wires, okay. So first thing is that strain at the time of failure should be very large, okay. So this is not the ductile material, let us take another example, okay. So if I have a material which has stress strain curve like this, okay, let us say stress strain curve is like this, okay. So here in this material, let us say it is having large elastic strain but very less plastic strain, okay. So plastic strain is very less, plastic range is very less. So what will happen to this material? So if I start elongating this material, it will keep on elongating, so keep on elongating, strain is increasing, but as soon as I get here, what will happen? If I release the stress, it will regain its original shape and size, okay. So it cannot be permanently drawn into the cross section of thin wires, okay. Only this much plastic strain is available, okay. So this type of material will also not be ductile, okay. So for ductility, for property of ductility to exist, the material should have a large plastic range, okay. So materials which are having large plastic range are called as ductile material, and materials which are having less plastic range, less elastic range, they can be broken down at, they fracture at very less strain, okay. Those materials are called as brittle material, okay. So what is the property of ductility? So ductility is the ability of a material to be drawn into thin wires, okay. So what is ductility? It is the property of material It is the property of a material to be drawn into thin wires by applying tensile load, the tensile forces. Okay, so under the action of tensile forces, these materials should be able to be drawn into the cross section of thin wires. Okay, now I have told you that for this property, plastic range should be large. Okay, so this property will exist in the materials which are having a large plastic range. Okay, so this property will be found in materials having large plastic range. Large plastic range. Okay, so that property is called as ductility. Okay, let's move on to the next property, brittleness. So what is brittleness? Brittleness is the property, as I have discussed in this, ductility only. So if the material will fracture under a very less amount of strain, then that material will be called as brittle material. Okay, so consider a rock. Okay, there is a stone. So if I try to elongate, it will not elongate. Okay, it will not elongate. If I keep on increasing the force, so stresses will be increasing, but strains will be very less. Okay, and suddenly it will fracture. It will break down into two pieces. Okay, so the strain at the time of fracture will be very less. Strain at the time of fracture will be very less. Okay, so stone can be called as brittle material. Same thing with concrete. Concrete will also undergo very less strain and it will fracture at very less strain. So these types of materials are called as brittle materials. Okay, so brittleness is the property. What is the property? It is the property by which material will fracture under very less amount of strain. Okay, so brittleness, it is the property due to which materials will fracture under very less amount of strain. Okay, clear? So this is the brittleness. Let's move on to the next property, malleability. Okay, so malleability is the property by which a material can be spread out in different directions by compressive loading. Okay, so if I apply compressive loading on a material, what will happen? If it is able to be stretched out in different directions, or it can be formed into a section of thin plates. Okay, it can be formed into thin plates by compressive action, by compressive forces, then that material is called as ductility. So what was the property of that? Property is called as malleability. Sorry, I think I said ductility. That property is called as malleability. So ductility was property of large plastic strain in tensile loading. Malleability is the property of large plastic strain in compression. Okay, so if I apply tension load and the material undergoes large plastic strain, then that material will be called as ductile material. And if I apply compressive load and the material is able to undergo large plastic strain, then that material will be called as malleable material. So ductile material, large elongation, large plastic strain in tension; malleable, large plastic strain in compression. Okay, so malleability, what is the malleability? It is the property, by which materials can be deformed into thin plates can be deformed into thin plates. Okay, so materials can be deformed into thin plates. Okay, right. So when materials can undergo large plastic strains, in compressive loading, then those materials are called as malleable. Those materials are called as malleable. Okay, so ductility is large plastic strain in tension, malleability is large plastic strain in compression. Okay, so malleability is also complete. Now let's come to creep. Okay, so all these properties that we have seen, these are the short term properties. Okay, short term properties means the period of application of load was very less. Okay, so suppose I am having a material like this. Okay, so if I apply, let us say I am applying compressive loading. Okay, so when I am applying compressive loading, I am taking the elongation or compression or whatever is the effect of those force in a very short term. Okay, in 5 up to 5 minutes I am checking. Okay, whatever testing time is there, this is 5 minutes or 10 minutes maximum. Okay, so till now what I have seen were the short term effects. Okay, either it was elastic deformation or plastic deformation, I was looking at the short term. But in structures, in civil engineering, in mechanical engineering, many structures are loaded for a very long period of time. So the long term effects will be very different from the short term effects that we have seen till now. Okay, so suppose if I am having a material and I have applied loading for very long period of time, then what will happen? Okay, so let us that property of creep is long term effect. Okay, so let us say I am having a material, I am having a prismatic bar, and on this prismatic bar I have applied a loading for long term. Okay, this load P I have applied. Okay, so at top this is fixed and at bottom I have applied a constant load P. Now this load I have applied within elastic limit. Okay, the load is within elastic limit, and what I am going to do, I am applying load. Okay, so when I have applied this load within elastic limit, in short term what will happen? This material will go instantaneous elongation like this. So let us say this elongation is instantaneous elongation or elastic elongation. Okay, this is elastic deformation. This is elastic deformation and this will be instantaneous. Okay, so as soon as I apply a load on this material, this will elongate. How much? Delta is equal to PL upon AE, that we have seen. Okay, so this elongation will be elastic elongation instantaneous. Now if I remove the load, since this is elastic deformation, after removing the load, this all extra elongation that was there, this will be removed. Okay, this will go and material will regain its original shape and size. Now this was the short term effect. But if we see the long term effect, after long term, maybe 10 years, 20 years, after 30 years, if we come again and this load was constantly applied for this much long period of time, what we will see that this material has gone some extra elongation, some extra deformation has occurred in the material, and that extra deformation is plastic deformation. Okay, this extra deformation is plastic deformation. Okay, so this was the instantaneous elongation, and now this deformation is called as creep deformation. This is now creep deformation. Creep deformation, and this is instantaneous, this is long term, and this deformation is plastic. This is plastic deformation. Okay, so load is within elastic limit, but The long-term effect of load, we are seeing that some additional deformation, some extra deformation has occurred into the material because of this long-term effect. Okay, so this deformation is called as creep deformation, or simply we call it as creep. So why it is necessary to consider creep deformation? Because in civil engineering, the structures are loaded for a very long period of time, and if we consider only elastic deformation, then we might not be safe. Okay, they might there might happen some extra deformation also, and because of that, serviceability criteria might get affected in the long term. Okay, so that's why creep deformation comes into picture, and while designing it becomes necessary. So all these things that are necessary in designing, that we are seeing, that we study in strength of materials, right? So RCC design, steel design, all these things will come into picture when we will study those subjects, right? Okay, so creep deformation, I hope you have understood what is the creep deformation. It is the long term effect of applied loading. So when we apply a load, there is some extra deformation in the material that is over and above the elastic deformation, and this deformation is plastic deformation. This is not recoverable, right? So even if we remove the load, even if we remove the load, elastic deformation will be recovered, but this plastic deformation will still remain. It will not be recovered. Okay, so creep, clear? What is the meaning of creep? I hope meaning of creep is clear. So write down, it is the additional deformation additional means over and above, over and above the elastic deformation, due to load applied due to sustained loading, due to sustained long term elastic load, okay. So it is the additional deformation over and above the elastic deformation due to sustained long term elastic load. Okay, that is the creep, and creep deformation is termed as plastic deformation. Okay, so this deformation is plastic deformation. This deformation is plastic deformation. Okay, or it can also be called as plastic deformation due to sustained loading. It can also be called as plastic deformation due to sustained loading. Okay, so this is the creep deformation. Now if we see the graph of creep deformation, it will be something like this. Okay, so if we look at the graph of creep deformation, let us see how we will get the graph of creep deformation. So let us say I have applied a gradually applied load. I have already told you what is gradually applied load. You must have seen the lecture. So gradually applied load takes some time to apply. Okay, so this is, and here we are having the time on x-axis, we are time, and here we are having strain. Okay, so creep can be measured in terms of deformation also, and creep can be measured in terms of strain also. Okay, if we measure in terms of strain, we call it as creep strain, or if we measured in terms of deformation, we call it as creep deformation. Okay, so at time t naught, when I have applied gradually applied load, so gradually applied load will not be applied suddenly, it will take some time. Okay, so at time t is equal to t naught, what will happen? At time t is equal to t naught, slowly and slowly we have increased the load from 0 to some value, some definite value. Okay, and the strain is also increased like this. So epsilon naught is the strain at that time. Okay, and then what will happen? I have let the load remain applied on the material. So strain will keep on increasing. Strain will keep on increasing. Earlier, it will increase at a faster rate. Strain will increase at a faster rate. Suppose for 1 year, it is increasing by this rate. After first year is completed, in second year, it will increase with a reduced rate. In third year, it will increase at a reduced rate. Okay, so rate of increase of creep deformation will keep on reducing, and ultimately it will remain, it will become constant. Okay, so this is called as ultimate creep strain. This will be called as this maximum value. After maximum value is reached, it will not increase further. Okay, so this will be called as ultimate creep strain. Ultimate creep strain, and this is what? Instantaneous elastic strain. Instantaneous elastic strain. Okay, so as the time is increasing, so this was this much strain happened at time t is equal to t naught. So when we have applied gradually applied load, slowly and slowly we have increased up to this amount, so there was an increase in strain. Okay, so this strain was instantaneous. Okay, instantaneous elastic strain. So if I have applied this load and after t naught, if I remove the load, this material will recover and the strain will become 0. Okay, but I have let this load applied for long period of time, for 1 year, 2 year, 3 year, 4 year, 5 year, 6 year, 7 year, 8 year, and so on. Okay, so slowly and slowly the creep deformation is increasing, and ultimately after reaching an ultimate value, it will remain constant. Okay, so this will be called as ultimate creep strain. So this much strain. Okay, and now if I talk about strain at any instant of time, so at any instant of time, let us say at time t is equal, at time t, at time t, okay, this will be the creep strain at creep strain at time t. Okay, so creep strain will always be lying between 0 and ultimate creep strain. Okay, so this will always be between 0. So if we are looking at instantaneous, at just when we have applied the load, just we have finished applying the load, creep strain will be 0. Okay, and if time is passing, so ultimately ultimate creep strain will be this much. So at any instant of time, the value of creep strain will be between 0 and this value. Okay, so this is the ultimate creep strain, and here the creep strain is 0. Here only instantaneous elastic strain is existing, right? Okay, very good. Now you will ask, sir, on what factors does this creep strain depends? Okay, this ultimate creep strain or creep strain depends on what are the factors on which it depends? Okay, so let us see all those factors on which creep strain depends. Okay, so factors affecting creep. So let us see what are the factors that are affecting the creep. Okay, so the factors that will affect creep are, first of all, loading. Loading. If more is the loading, higher the stress, higher will be the creep strain. Okay, then temperature. Temperature will also affect creep. So if I am having higher temperature, then creep strain will be larger. At lower temperature, creep will be lower. Okay, then it will also depend on type of loading. Type of loading. Okay, that is static or dynamic. So loading is coming again and again, or it is or it is static. Okay, so on all these factors the creep strain, ultimate creep strain depends, right? Okay, so creep strain depends on these factors. Let's move on to next, relaxation. Okay, so relaxation is also related to creep only. What happens in creep? In creep, what happens if I am having any material? In creep, what happens if I am having any material and on this material I have applied a continuous sustained loading? Then what will happen? Because of this load, there is stress is constant. Stress is constant and strain increases. Strain increases, right? So this is in creep. This happens in creep. Now what happens in relaxation? Relaxation is similar to creep but happens opposite. In relaxation, strain is constant but stress reduces. Strain is constant but stress reduces. Okay, so what will happen? What will happen in relaxation? So here I am having a bar. Okay, I am having a bar, and what I will do, I will increase its length. Okay, so earlier the bar length is this much. This much is the length of the bar, and what I will do, I will provide some strain. I will increase its length, and then I will fix this bar. Okay, fix this bar to another support. Okay, so this bar was originally having this much length. Okay, so original length was this much. This was the original. This was the original length of the bar. Okay, and what I have done, I have increased the length by delta L. Delta L. So strain in this case will be, strain is equal to delta L by L. That will be constant, and the stress will keep on decreasing. So if I, this is relaxation. Okay, so if I am looking at this material instantaneously, at that instant, if I check what is the stress will be, let us say, 100 Newton per mm square. Now I have kept the strain constant and stress initially is 100 Newton per mm square or 100 megapascal, let us say. Okay, now after 1 year if I will come, I will see that stress has reduced somehow. Little bit stress is reduced. I will, if I come after 5 years, I will see stress is even more reduced. So with constant passage of time, I will see that there is reduction in the stress value even though strain is constant. So at constant strain, there will be reduction in stress value. That property, that thing, we term as relaxation. So the material was initially very highly stressed, now has somewhat relaxation in the stress value. Okay, it has somewhat relaxed. Okay, so if you are having a daily load of 100 questions, let us say, so initially at the first day when this 100 questions will come, you will feel very stressed, but as slowly you will progress, you will think, you will see that you are habituated of it, so stress will reduce. Okay, even though the load, the amount of pressure that is coming, that will be constant, but you will be able to handle it better. So material will also undergo some relaxation, the stress value will reduce. Okay, so this is similar to relaxation. Okay, similar to relaxation, right? Here stress is constant and strain is increasing. Okay, now if I want to replicate these two, okay, if I want to change, if I am allowed to change some parameters in the relaxation and make it exactly similar to creep, what I will do, as some amount of stress is decreasing, what I will do, I will pull it little more, so that stress increases again to that constant value. Initial stress was 100 megapascal. Okay, let us say after 1 year when I came, let us say the stress was 99.5 megapascal. So what I will do, I will pull it a little bit more, so that stress again increases to 100 megapascal and strain is now increased. So it has become similar na, strain increased but stress constant. After 5 years when I come again, I'll see that again the stress has reduced to 99.5 megapascal. So what I'll do, I will again increase some length. So strain is again increased and stress I have made again 200 megapascal. So these two are similar phenomena. Okay, so here what is happening, load is applied in such a way that stress value will not reduce. Okay, stress value will not reduce, stress value will remain constant, strain will keep on increasing. And here I have put this like this, the constraints are like that, that strain is constant. Okay, so change in length is constant, so because of that the stress will keep on reducing, although they are very similar to each other. Okay, clear? So what is the difference between creep and what is relaxation that you have understood? So both are actually in a same phenomena. Okay, the how they are applied are different. Okay, clear? So relaxation is also clear. So let's no need to write down the definition if you have understood. Okay, let's move on to the next one. So next is fatigue. Now fatigue is also very important when it comes to cyclic loading. Many a times a structure will be subjected to cyclic loading or repeated loading. In those cases fatigue is very important. Okay, you must have seen an example that there is certain wire. Okay, so when you are not able to break that wire, okay, it is very, you know, strong. Okay, so if you are bending it, you are not able to bend it completely that you are able to break it. So what you do, you bend that wire in one direction, then bend that wire in another direction, then bend that wire. How much you are able to bend, that much you bend. Okay, so you bend it again and again and again and again and again and again, repeated loading, cyclic loading you are providing, and after some reversal of cycles you will see that that wire has become, that material has become weak, and then suddenly it will break. Okay, so this is because of fatigue. Fatigue means because of repeated loading the material is becoming stronger. So it is the deterioration of material under the repeated loading or cyclic loading. So reduction of strength of the material or deterioration of material under repeated loading or cyclic loading, that is called as fatigue. Okay, so what is fatigue? Fatigue, it is the reduction in strength of material, it is the reduction in strength of material, or we can also call as deterioration. Deterioration. Deterioration means somehow the material was good, now it has reduced in some ways. Okay, that is deterioration. So deterioration, reduction in strength of material or deterioration of material under repeated cyclic repeated cyclic loading. Okay, so if I provide, so material was initially very strong. Okay, suppose this material has a strength of 100 megapascal. Okay, so I'm not able to apply stress of 100 megapascal, I'm able to apply stress of only 70 megapascal, let us say. So when I'm applying the stress of 70 megapascal, it will not break definitely, but what I will do, I will reverse the stress in another direction. So again I have applied 70 megapascal, 70 megapascal, 70 megapascal, 70 megapascal, and like this I am repeatedly applying the stresses of opposite nature repeatedly again and again and again. So what will happen, slowly and slowly what will happen, the strength of the material will reduce, and it will, when it will become less than 70 megapascal, it will suddenly break. Okay, so this is the fatigue. Now if I am able to apply, in this example I have told you 70 megapascal, and because of that 70 megapascal, let us say I had to apply repeated stress 100 times, let us say 100 times, but let us say I am stronger. Okay, if I am, so at 70 megapascal number of cycles are 100 cycles. Okay, but if I am able to apply 80 megapascal strength, okay, 80 megapascal stress if I am able to apply, so will I need to again apply number of 100 cycles, or in less cycles I will be able to break it? In less cycles I will be able to break it definitely. So now the cycles will be less than 100 if I'm able to apply 80 megapascal. So in 80 megapascal stresses, number of cycles required are less than 100, less than 100 cycles. Okay. Now, if I am able to apply 90 megapascal stress, this value or this number of cycles will be even less. Okay. Now, if I'm able to apply only, let us say 60 megapascal, then maybe I have to apply that loading 500 times. Okay. So we can get a curve between the stress applied and the number of cycles required to produce fracture or to break the material. Okay. That, and we can draw the curve between them. We can draw the curve between them. That curve will be called as SN curve. Okay. So here we are having stress. In this case, we'll represent stress by S, and here we are having number of cycles represented by N. Okay. So SN curve will be something like this. SN curve will be something like this. So after a while, it becomes horizontal. Okay. So here, what this curve is representing, if I am applying very high stress, then number of cycles required are less. If the stress is reducing, then number of cycles required to produce fracture are increasing. Okay. So here number of cycles are even more. Here number of cycles are even more, and there will be some value of stress. After which or below which the material will not fail even if I apply infinite number of stress cycles, and that value is called as endurance limit or fatigue limit. This is called as endurance limit or fatigue limit. Okay. So as you can see, endurance limit is much less than the strength of the material. So actual strength, if I apply just one cycle and it will break, okay, that strength is represented here, and this endurance limit is much less than the stress value, actual strength of the material. Okay. So what is the meaning of endurance limit? Meaning of endurance limit is that if I apply even infinite number of stress cycles, then also material will not break. Let us take again the example of this wire only. Okay. So if I am applying, let us say the strength is 100 Newton per mm square. Okay. So if I am applying a stress of, let us say, 1 Newton per mm square, again 1 Newton per mm square, again 1 Newton per mm square, do you think even if my 10 generations keep on applying the load 1 Newton per mm square, will it break? It will never break. So there is a certain stress limit below which material will never break, even applying the infinite number of stress cycles. So that limit is called as endurance limit or fatigue limit. Clear or not? Okay. So what is the meaning of fatigue? Fatigue means if I am applying repeated loading or cyclic loading, the material will reduce its strength. Okay. There will be a reduction in the strength of material, or there will be deterioration of material. That is called as fatigue. And what is the endurance limit? Endurance limit is the stress level below which the material will not break or material will not fail even if we apply large number of stress cycles. Sometimes in questions they give large number of stress cycles, and sometimes they give infinite number of stress cycles. Okay. So both are correct. So let us write down endurance limit. Endurance limit. Write down, it is the stress below which the material will not fail even after even even at infinite number of stress cycles. Finite number of stress cycles. Or sometimes in the question they will say it is the stress, it is the stress at which material will fail at large number of stress cycles, large or infinite number of stress cycles. Okay, so do you find these two statements contradicting each other? Here we are saying material will not fail, and here we are saying material will fail, okay. So do you find these two statements contradicting each other or they are same? In question sometimes it is asked material will not fail, that answer will be endurance limit, okay. In question sometimes they ask the statement material will fail, and again the answer will be endurance limit only, okay. So for both of them, material will not fail, the answer will be endurance limit, and material will fail, again the answer will be endurance limit only. Why so? Because they seems to be opposite of each other, but they are not opposite, they are saying the same thing, okay. Suppose you propose to a girl, okay, and she says yes, I accept your proposal, but I will marry you after infinite number of years, okay. And the girl says, suppose I will marry you after infinite number of years, or if she says I will not marry you even after infinite number of years, the answer is same, that she has rejected the proposal, okay. Same thing is like this, that material will not fail even after infinite number of stress cycles, then also material is not failing actually. And if they are saying that material will fail at infinite number of stress cycles, that means the result is same, the answer is same, that material will not actually fail. If we say that material will fail at infinite number of stress cycles, the implication is that the material will not fail, okay. So that means both the statements are implying the same thing, and the answer to both the statements will be endurance limit only, okay. Clear? Okay, so this is the fatigue and this is the endurance limit. Let's move at the next point. Next is resilience, okay. Now what is resilience? Resilience is the strain energy stored in the material, okay. So if we apply some load on the material, and because of this load there will be deformation in the material, and because of that deformation there will be some strain energy stored in the material. Now the strain energy stored in the material will be equal to the external applied force, okay. Now right now we are interested in the strain energy stored in the material. So when we are applying the load, material is getting deformed, and there is some strain energy stored in the material, okay. Now resilience, okay, how much if we apply larger amount of force, larger deformation and larger strain energy will be stored, okay. So there are two terms, resilience and toughness. Resilience represents the strain energy stored within the elastic limit or up to the elastic limit. So strain energy stored in the material up to the elastic limit will be called as resilience, okay. So if we are loading the material up to elastic limit only, then the amount of strain energy, the value of strain energy that is stored is called as resilience, okay. And suppose we are loading within elastic limit, and if I remove the loading, what will happen? The strain energy that we stored in the material when we were applying the load, now when we are removing the load, that strain energy is getting released, because the material will come back to its original dimensions, original shapes, original state, right? So when material will come back to its original state, in original state there was no strain energy stored in the material. So what material has done, material has released its entire strain energy that was stored while we were loading. So while loading, the material is storing the strain energy within itself, and when unloading, material is releasing back that strain energy, okay. So this property of material is called as resilience. So when the material So resilience is the property by which we can store the strain energy in the material while loading, and having that strain energy recovered while unloading is called as resilience. Is it clear? Let me explain again. Resilience is the property by which we can store the strain energy in the material and recovering that strain energy back while unloading the material. That is called as resilience. And resilience will happen only when we stress the material within the elastic limit. If we stress the material within elastic limit, then only resilience can happen. Then only the strain energy stored will be called as resilience. Okay. Otherwise, it will go beyond the elastic limit. Then we cannot recover that strain energy, right? So it will not be called as resilience. Okay. So resilience. Let us write down what is the meaning of resilience. Resilience. Write down. It is the property of material. It is the property of material by which strain energy can be stored in the material upon loading, and having that strain energy and having that strain energy recovered strain energy recovered upon unloading. Okay, so this is called as resilience. So resilience we can also define as the amount of strain energy stored, the amount of strain energy stored in the entire volume of the material, in the entire volume of the material within elastic limit. Elastic limit. Okay, so this is the resilience. Now mathematically it can be represented by the area of stress strain curve in P delta curve. Okay, so write down, mathematically it can be represented mathematically it can be represented by the area of load deflection curve, or we can also say P delta curve within elastic limit, within elastic limit. Okay, so if we are having a load deflection curve, if we draw the load deflection curve, then the strain energy stored within elastic limit will be, okay, so let us say this is the elastic limit. Here we are having B. Okay, here is A, proportional limit. Okay, let us not write A, proportional limit. Let us just write B, elastic limit. Okay, so strain energy stored within elastic limit. Okay, so area of stress strain curve under load deflection curve within elastic limit. This will be called as resilience. And resilience is nothing but the total strain energy stored. So total strain energy stored is termed as U, capital U will be, and when it is representing the energy up to elastic limit, that is called as resilience. Okay, so that strain energy. So this is what the total strain energy stored in the material. Okay, this area is giving the total strain energy stored in the material up to elastic limit. The point B is elastic limit. Elastic limit. Okay, and this is the value of resilience. This area will give you the resilience, and this graph is drawn between load deflection curve. This is P load and this is delta deflection. Okay, now sometimes this material will be linear elastic material. Okay, sometimes this material will be linear elastic material. So for linear elastic material, the load deflection curve will be straight line. Okay, load deflection curve will be straight line for linear elastic material. So for linear elastic material, the stress strain curve will be something like this. Okay, so this will be linear elastic material. Okay, so this is load P, this is delta deflection. So for linear elastic material, we are having this load deflection curve. Clear? Okay, very good. Now, since this load deflection curve is like this, okay, so this is the elastic limit. This is the elastic limit, and within elastic limit, whatever the total amount of energy is stored, this whole area will be called as resilience. This will be called as resilience. So mathematically, how we can represent resilience for linear elastic material? So for linear elastic material, we can derive the direct formula. This is the area of the triangle. Area of the triangle can be derived. Okay, it is very simple. Okay, so for linear elastic material, let us say we have loaded up to load P and the deflection is coming out to be delta. For this, we don't know the equation of this curve, so we cannot calculate this area. Okay, but we can easily calculate this area. So that means for linear elastic material, modulus of resilience. So capital U is representing the total strain energy stored in the material and R is representing the resilience. We are calculating under the elastic limit. So it will be half P delta. What is the area of triangle? Half P delta, right? So this is half P delta. Clear? Okay, so this will be the total strain energy stored in the material up to elastic limit. Okay, so this is the resilience. Let's move to the toughness. Resilience, I hope clear to all. Okay, next property is modulus of resilience. Okay, so modulus of resilience, how we have defined the resilience? Resilience is defined like this. Okay, now modulus of resilience is simply resilience per unit volume, or we can say total strain energy stored in the material up to elastic limit per unit volume of the material. Okay, so when I'm applying load on this material, let us say when I'm applying load on this material, I have applied load up to elastic limit. I can calculate what is the total amount of strain energy stored in the material. Now total strain energy stored in this entire volume of material up to elastic limit will be called as resilience. But when I divide that value of resilience by this volume of the material, so resilience per unit volume will be called as modulus of resilience. Is it clear? So resilience is what? Total strain energy stored in this entire volume of material. That will be resilience. And if I take that value per unit volume of the material, then it will be called as modulus of resilience. Clear? So what is the modulus of resilience? That is clear to you. Okay. So modulus of resilience, it is the strain energy stored. It is the strain energy per unit volume strain energy stored per unit volume of the material up to elastic limit. Okay, per unit volume up to elastic limit. Okay, so modulus of resilience can be defined as modulus of resilience can be defined as resilience per unit volume of material. Resilience per unit volume of the material, that will be resilience. Okay. Right. Okay, so this is the modulus of resilience, right? Now mathematically, how we can represent resilience? Mathematically, it can be represented by area of stress strain curve, area under the stress strain curve up to elastic limit. Okay, so mathematically modulus of resilience, modulus of resilience, and here modulus of resilience will be represented by small u r. Small u is strain energy per unit volume, small u strain energy per unit volume, okay, and capital U is total strain energy. So if we are writing capital U, we are denoting the total strain energy stored in the material, and if we are writing the small u, it will be representing strain energy per unit volume. Okay, so mathematically modulus of resilience can be represented by area of stress strain curve, area of stress strain curve within elastic limit, within or up to elastic limit, within elastic. Okay, so let us represent the resilience also, or modulus of resilience also. So if I draw the stress strain curve of the material, so let us draw the stress strain curve of material. Now we will be studying only linear elastic materials. Okay, we will be studying only linear elastic materials. Okay, we don't study here non-linear elastic. Okay, so Hooke's law will be valid always. Hooke's law will always be valid. So for a linear elastic material, we will be getting straight line. Okay, and this is the graph between stress strain curve. Okay, so let us say up to here we are having sigma y, and here we are having the strain. Okay, this is the yield stress. Now you might say, sir, why we are using sigma y? Sigma y represents yield stress, right? And we are saying that strain energy stored up to elastic limit or within elastic limit. So you have already told, sir, elastic limit and yield stress limit, these are different. But for linear elastic material, I have also told you that proportional limit, elastic limit, and yield limit, they are same. They are same. Okay. So yield stress will be representing the elastic limit also. Okay. So the area that is stored within elastic limit, that means this area will represent what? Modulus of resilience. Okay, this area will represent, writing was not coming good with red pen, let me try this orange pen. Okay, so this will be modulus of resilience in bracket R. Okay, so this is the modulus of resilience. Now for linear elastic material, we can write the mathematical expression. Okay, for linear elastic material, linear elastic material, modulus of resilience is equal to half stress into strain, half stress into strain, that means area of triangle, half base into height, half stress into strain, that will be the area of triangle. Now strain can be represented as half sigma y. Okay, now strain can be represented by stress upon Young's modulus. Okay, so this at this location we are getting the yield strain. Okay, so yield strain will be equal to sigma y by E. Okay, so if we replace this, we will get half we'll get half sigma y into epsilon y will be sigma y by E, sigma y by E, Young's modulus. Okay, so we'll get this as sigma y square upon E. Okay, sigma y square upon. So this formula is important. You have to remember this formula. Okay, so remember this formula for modulus of resilience, and also remember this formula for modulus of resilience. Okay, both these formula are representing the same thing, but both are important. Okay, you have to remember both of these formula. Okay, clear? So this is the modulus of resilience. Now if you want to write down resilience in terms of stress and strain, so resilience will be modulus of resilience into volume. So that means you can write it like this: sigma y square upon 2E into volume. That will be the value of resilience. That will be the value of resilience. Okay. Now sometimes in some books they are defining this term by proof resilience. Okay, so proof resilience and resilience are same thing. Okay, in some Indian authors books they have defined proof resilience as a separate term. Okay, but in foreign authors book the term proof resilience does not represent anything. It is not given in any foreign author book. Okay, in Indian author books they have defined a separate term, that is modulus of resilience. Okay, sorry, proof resilience they have defined. Okay, now let's move on to the next property, that is toughness. Okay, so toughness, what is toughness? Toughness is again strain energy stored in the material or strain energy stored in the total volume of the material. So that is called as toughness. But resilience was up to elastic limit only, but toughness represents the total strain energy stored in the material up to fracture point. Okay, so when we define total strain energy stored up to elastic limit, then it will be called as resilience. But when we define total strain energy stored up to fracture point, this whole energy will be called as toughness. Okay, so difference between resilience and toughness is just that resilience is the total strain energy up to elastic point, but toughness is the total strain energy up to fracture point. Okay, so let us write it quickly. Since we have understood resilience, now toughness is not that difficult. Okay, so it is the total strain energy stored in the material, total strain energy stored in the material up to fracture point. Okay, so if I want to draw or I want to represent it mathematically, then toughness will be represented by this area under load deflection curve, up to fracture point. So this entire will be represented by this will be toughness. Okay, so this is load deflection curve. Okay, so total strain energy stored in the entire volume of the material up to fracture point will be called as toughness. Now there will be another term, modulus of toughness. So modulus of toughness will be what? Total strain energy per unit volume of the material up to fracture point. Okay, so it will be the strain energy stored per unit volume of the material, strain energy stored per unit volume of the material up to fracture point. So here in this case, the area of stress strain curve will represent the area under stress strain curve. So let us say this is the stress, this is the strain. So area under stress strain curve will represent the modulus of toughness. So this area will be represented by, this area will be modulus of toughness. Modulus of toughness, right? So this is the modulus of toughness. Okay. So modulus of toughness is also clear. Now there is a common question that modulus of toughness of mild steel is greater or modulus of toughness of high yield strength or high strength steel is greater. Okay. So what will be the answer? Answer will be modulus of toughness of mild steel is greater than that of high strength steel. Okay. So write down this point. Modulus of toughness of mild steel is greater than modulus of toughness of high strength steel. High strength steel. We can verify it by stress strain curve of mild steel and stress strain curve of high strength steel. Okay, so stress strain curve of mild steel will be something like this, and stress strain curve of high strength steel will be something like this. Okay, so this is the stress strain curve of high strength steel or high carbon steel, high strength steel, same. And this is the stress strain curve of mild steel. Okay, so since the modulus of toughness represent the strain energy stored up to fracture point, so this area will represent, let me change the color, let me keep the color same as the curve. Okay, so it will be easy to understand. So this area is representing modulus of toughness of mild steel, and this area is representing the modulus of toughness of high strength steel. So by visual inspection only you can say that this area of mild steel is greater. Okay, so modulus of toughness of mild steel is greater than the modulus of toughness of high strength steel. Okay, so we can say mild steel is more tough than high strength steel. Clear? Then proof resilience. Proof resilience is nothing when resilience is found by proof stress method. Okay, or it is same as resilience. Okay, nothing difference, but some Indian authors say, in Indian author book they say resilience is when the strain energy stored is within the elastic limit or less than the elastic limit up to any point. But proof resilience is just at the elastic limit, when we have loaded up to the elastic limit, just toward to the elastic limit. But in foreign authors book there is no distinction between resilience and proof resilience. Okay, so you can write same as resilience, nothing different from resilience. Okay, proof resilience is same as the resilience. So in Indian authors books they have defined it separately. Okay, nothing, no distinction as such. Okay, now let's move on to the next property, that is Boschinger effect. Now Boschinger effect says, see what Boschinger effect says, let us understand. There is stress strain curve of the material. Okay, stress strain curve of the material, let us see. Okay, and stress strain curve of the material, let us say this is like this. Okay, so in this material, this is the elastic limit. Let us say this is the elastic limit. Point B, elastic limit is this. Now, if I load this material up to this point, okay. So when I load this material up to point B, up to elastic limit, and when I unload the material, what will happen? The unloading curve will be same as the loading curve. So unloading curve will be like this, and since I have loaded within elastic limit, the material will regain its original shape and size. Okay, but if I load beyond the elastic limit, what will happen? The material will be loaded up to this point, and now the unloading curve will be different from the loading curve. Okay, now this will be the unloading curve of the material if I load beyond elastic limit. And what will happen? there will be some permanent deformation. So this much deformation will be permanent deformation. But after unloading, this is the permanent deformation. When I load again, then loading curve will be again this much. And now this has become my new elastic limit. Okay, this is D dash, this is new elastic limit. Okay, so that means I can say my elastic limit has now increased or not. My elastic limit has now increased. Okay, so elastic limit is now increased. That means I have made the material a little bit stronger. My material is now becoming strong. Okay, so if I do it more, my material will become even more strong, elastic limit will be raised further. So can I do this again and again and increase the strength of the material? The answer will be I should not do that. Why? One thing is that the plastic deformation range is getting reduced. Earlier, the plastic deformation range was this much. Now, after I have raised the elastic limit, my elastic or plastic deformation range is reduced. Okay, so I am reducing the plastic deformation range every time, but this is not Bochinger effect. What Bochinger pointed out, that Bochinger has said that when you have raised the elastic limit in one direction of the loading, in other direction what will happen? In other direction, let us say this was tension, and what will happen in compression? In compression, what will happen? If earlier the elastic limit was this much, here in compression, now when I have increased the elastic limit in tension, my elastic limit in compression has reduced. My elastic limit in compression has reduced. This is the Bochinger effect. So elastic limit in compression has reduced. This is the new elastic limit. Okay, so elastic limit is tension is raised. So when I am cold working, okay, elastic limit in tension is raised, but now because of that, elastic limit in compression has reduced. So this was the earlier elastic limit. This was the earlier elastic limit. Now the elastic limit is reduced. Okay, so what is the statement of Bochinger effect? That increasing yield stress in the direction of applied in the direction of applied force by cold working. This is called as cold working. Okay, by cold working reduces the yield strength in opposite direction, in opposite direction. So this is called as Bochinger effect. So I have increased the elastic limit or yield strength in one direction of applied loading. So in opposite direction, it will be reduced. Elastic limit will be reduced or yield strength will be reduced, right? So this is the Bochinger effect. Then let's come to annealing. In annealing, what we do, see, when I have cold worked the material, okay, so by mistake or due to when load were exceeded beyond the elastic limit, my ductility was reduced, okay. Then I call this type of material as cold work. My yield strength is increased and my ductility is reduced. So this type of material is called as cold worked, okay, or work hardened material. So in the work hardened material, if I want to restore the ductility and malleability, what I will do, I will heat that material to recrystalline temperature and then slowly I will cool it down. So when I heat it to the recrystalline temperature, what will happen? All these effects will be gone. Okay, at very high temperature, I have heated like 700, 800 degrees Celsius. So at that temperature, material will restore its original properties, and these effects of cold working and work hardening effects will be gone away. Okay, so I will be able to restore the ductility of the material. Okay, so annealing, it is the process. It is the process of heating the material heating the work hardened material to recrystalline temperature to recrystalline temperature and slowly cooling it down to restore its malleability and ductility. Malleability and ductility. Okay, so this is the process of annealing. I have heated the material to recrystalline temperature and then slowly I have cooled it down, so my ductility and malleability of the material are restored. Okay, now hardness. Hardness is the surface property of the material. If my material is hard, it is very difficult to make scratches or indentations on the surface of the material. So this property by which I cannot make, or the material can resist the scratches and abrasion and indentations, that is called as hardness. So hardness is the surface property, right? Okay, so hardness, it is the property. So sometimes you might have heard the expression that from the outside he is hard, but from inside that person is soft. Okay, so if the person is hard from outside, that means hardness is the surface property. Okay, so on the surface he looks hard, but inside he is having soft heart. Okay, so that is the hardness. So for material also, so it is the surface property, or it is the property of material, property of material by which the material is able to, by which the material is able to resist scratches, abrasions and indentations Okay, next it is the surface property. It is the surface property. Okay, so this is the hardness. Let's move on to the next one, that is tenacity. Tenacity. So there are 17 properties that we have studied. So tenacity is the property that is used in textile industry. If we apply tension on a thread and it is very high strength in tension, it is showing very high strength in tension, that property is called as tenacity. Okay, so it is the property by which by which material can withstand high tensile stresses. Withstand high tensile stresses. High tensile stresses. Or it is also called as, or it is the ultimate strength in tension. It is the ultimate strength in tension. Okay, so all the properties that I have discussed in detail, you might have seen that today I have discussed some properties in much detail, and some property I have written just one line definition, little bit explanation. So it is because of that these properties are asked only one or twice, and just this simple language is asked. Okay, no need to discuss these properties in detail. Wherever detailed discussion was necessary, I have discussed those properties in detail, and you will not find any question which will be away from that. Okay, so yes, in fracture, in fatigue, one thing is important. Let me explain. In fatigue, yes, fatigue. So fatigue strength, it is important to note. What is fatigue? In fatigue, what happens if I am applying the cyclic loading or reversal of stresses, then what will happen? A microscopic crack, a little bit, very small crack will develop, and the propagation of that crack will increase. Okay, so that crack, with each repeated loading, the width of that crack will increase, and suddenly the width will become so long, so large, that the remaining material will not able to resist the applied load. Okay, so fatigue happens due to progressive cracking of the material. Okay, so fatigue results due to progressive cracking of the material. Okay, now that means if there is rough surface, in rough surface we will find an opportunity that crack will start from there. Okay, so polished surface will have high fatigue strength, okay. rough surface rough surface have low fatigue strength, okay. If I apply high value of stress, okay, high value of stress, that will result in low fatigue strength. Okay, high temperature this will result in low fatigue strength. Okay, so these are all the terms that are important for fatigue. Okay, all the properties I have discussed in detail. Okay, this much is enough for your examination. If any question comes from these properties, you will be able to easily solve that question. Okay, so that's now for today's class. Let's meet up in the next class. Thank you, GW soldiers. Take care.